Hello, welcome to another podcast. This is part two of resonance. So this is meant to follow the previous one. I'm hopeful that it won't be quite as long as the previous one, but we will see. Um, this one is more along the lines of applying resonance, whereas the previous one was just defining what resonance is. So just to rehash, resonance is the sharing of pi electrons. You can only share pi electrons through p orbitals, be it a overlapping neighbor, two pi bonds in a row, empty p orbital, a lone pair in a p orbital, anything as long as you're dealing with p orbitals that are adjacent to one another. Okay, so I want to start with a generic example and want to emphasize that we're going to consider the quality of resonance more so than the quantity. So in the textbook, they mentioned the more resonance structures you have, the more stable that compound will be, the more resonance contributors, the more it helps stabilize charge distribution. But I want to focus a little more on the type of resonance. So emphasize the fact that lone pairs can become pi bonds and pi bonds can become lone pairs. So I'm going to start and try something. And this is an approach that says it's okay to make a mistake as long as you catch your mistake. So a lot of the things we'll do, we're going to mess up at first, and that's fine. So we'll see if I mess up. I'm going to start with a lone pair on the right. I'm going to turn it into a pi bond. Okay, so I think that's what I'm supposed to do. Lone pair into pi bond. So far, so right. That's going to create a fifth bond to carbon. So I have to break a pi bond on carbon and move it somewhere else. And uh-oh, that's a sigma bond. That's a sigma bond. So if I were to do this, the only way that could work is if I broke a sigma bond. Sigma bonds do not break when you deal with resonance. So sometimes trying it and getting it wrong is as good as just knowing exactly where to start. So I know that I did that one wrong. So I'm going to try the other side. Electron donating group. So I'm going to go ahead and draw an arrow from the lone pair on X. Doesn't matter which one I choose. I'm going to choose this one. I'm going to draw it to the middle of the bond. So that shows a lone pair becoming a pi bond. So lone pair. Turning into a pi bond. Which means on the other end, I have to undo what I did. So a pi bond has to turn to a lone pair. So this pi bond, I'm going to start in the middle. It's going to end up, end up on the Y as a lone pair. So in that case, a pi bond is turning into a lone pair. This is pretty much it for resonance. As long as you can recognize that, we're set. So we're going to go ahead and send that bond over. Going to give it a name. So I want to emphasize now, I want to get rid of my drawing a little bit, but want to emphasize that there's two types. If a pi bond becomes a lone pair, the pi bond is breaking and pulling electron density away. So that's one type of resonance we're going to consider, and that is electron withdrawing resonance. It's pulling electron density away from the molecule and putting at an extreme end the atom at the termination of whatever the pi system is. So in this case, Y is taking electron density away. So we're going to refer to Y as an electron withdrawing group because it is ultimately accepting the electrons in the lone pair. Electron withdrawing groups will have a tendency to take on a negative charge. On the other end, the X, we're going to call it electron donating group because it is putting electron density into the system. It's adding it to. So when it loses those electrons, it should end up with a positive charge. So I'm going to go ahead and erase everything I've written. So now we have just a beautiful picture here. So in doing this, the electron donating group is now carrying a positive, electron withdrawing group is now carrying a negative. X and Y just represent any generic atom, not necessarily halogen, deuterium, just happen to be two letters I picked. Okay, so again, very important thing to note that on the donating side, a lone pair turned into a pi bond. On the electron withdrawing side, a pi bond turned into a lone pair. Okay, so we're good on this. Now it's time to consider which of these two resonance contributors is more stable. Okay, so rule number one, most important thing, make sure all second row atoms have octet obeyed. I put except hydrogen, not to say hydrogen is a second row atom, but hydrogen is one of the exceptions. Hydrogen just needs one bond. But NO and F, need to have octet rule satisfied. Have to have 8 electron pair or 8 electrons in the form of 4 pairs bonding or lone pair. So if I consider this, in the first structure, 1, 2, 3 lone pairs and a bond, so X is good. Y, lone pair, bond, and bond, so Y is good. Carbon 1, 2, 3, 4 bonds, all is good. In the second structure, central carbon, 1, 2, 3, 4 bonds, so it's good. X has 2 lone pairs and 2 bonding pairs, 2 bonds, so it's good. Y, lone pair, 3 lone pairs and a bond, 4 electron pairs, it's good. So the octet rule is satisfied for both structures. So next, and these are sequential, most important thing is to have the octet rule satisfied. The next, minimize number of charge sites. So charges equal reactivity. If you have a plus, something that's going to attack it. If you have a negative, it's going to try to share that negative. So you want to have as few positive charges and negative charges as possible. So the structure on the left, no charges whatsoever. Structure on the right has 2 charge sites. So because of that, we're going to refer to the one on the left as the so-called major contributor, the most stable of the various resonance structures, which in this case is just 2. The one on the right is just 1, just one minor contributor, just one major contributor, but the minor one in this case doesn't add as much to the overall structure as the major, meaning most of the time it's going to be in this form. Let's say 99%, 95%, all depends on what system I'm looking at, because I don't know the exact atoms, I can't tell you. But this is going to be the major contributor, all octet with no charges, all octet but with charges. And then last, if you have charges, you want to put them on the atom that can handle it more. So we're going to see through pattern recognition that oxygen has a tendency to take a negative, nitrogen has a tendency to get stuck with positive. Carbon can kind of go both ways, although it doesn't want to charge. Okay, so we have our basic guideline. Electron donating groups are where a lone pair becomes a pi bond. Electron withdrawing groups, pi bond becomes a lone pair. And then when trying to decide if it's a stable resonance contributor, octet rule first, minimize the charges. And if you happen to have a charge, it has to be on the site where it's most favorable. Okay, so onward we march. Okay, so determine whether the following pairs of structures are resonance structures of one another, and if they are, or if they are, explain why. If they're not, explain how or what, where it's violated. So considering this first structure here, it's known as acetone, carbonyl, C-double-O in the middle, 2 CH3 groups. Over here, this is called an ene-O. So in order to become a resonance structure, you just have to move pi electrons. So this bond is going up here. Used to be a double bond, sigma and pi. Now it's just a single bond, just a sigma. There's now a pi bond here, but I don't know what came in to go there. I can't really say like that because that's breaking a bond. There's no lone pair on carbon, so I can't really do that. So this cannot be. So this is known as is tautomers. So both, let me go back and get rid of my drawing and say, in this grouping right here, we went from a pi bond between carbon and oxygen and a sigma bond between carbon and carbon to now just only a sigma between carbon and oxygen and a pi bond between carbon and carbon. And this had 3 H's altogether. Now it just has 2, and this H is relocated. Because the nucleus moved, because hydrogen went from one atom to another, these cannot be resonance structures. So foreshadowing, but down the road, you're going to learn a term called tautomers. And you may have learned it in cell bio at this point, but it's a ketone and an enol. Okay, so those are not resonance structures. So I'm a little bit shaken by this one, but let me see if I can do okay. I want to put the lone pairs in. There's the lone pair on oxygen. That lone pair can donate in, and if it does, it can stabilize that carbon. So I don't want to go all the way to the carbon. I want to only draw it to roughly the middle of the bond. So lone pair becoming the pi bond. Wow, just there we go. So we have this signal bond now turning into a double bond. The positive charge, I want to make sure I put that remaining lone pair on oxygen. But this isn't a resonance structure because a lone pair became a pi bond, no nuclei moved. So H is in the same spot, carbon's in the same spot, O in the same spot, CH3, same spot. So that'll work. Okay, so let me get rid of my, I had it on, so let me clear it. And emphasize that this lone pair went in, formed that pi bond. So yes, it will. And I probably still want to put a lone pair on the product just to be a little more specific. Finally, the last one. This one is deceptive because it just looks like the pi bond moved over here, which maybe it could do. But anytime a pi bond moves, so if these electrons moved over here, you would have to get a positive and a negative at the respective sites. So when you move electrons, if it starts out neutral, you end up with charges. It starts out with charges, you could end up neutral, not necessarily every time. But I have to keep track of charges because no charge is being written here. This isn't a resonance structure. So what this is just the mirror image, the same compound but flipped around. So CH2, CH, CH3, CH3, CH, CH2. So they're not resonance structures, same structure but flipped over. So no pi electrons actually had to move. Okay, so I feel a little bit better. So now I want to apply it to specific examples. Draw all significant resonance contributors and determine the major contributor. So again, we're always going to consider lone pairs becoming pi bonds and pi bonds becoming lone pairs. So I need to draw in the lone pairs on oxygen and figure out what they can do. So I can bring a bond to this positive charge. That'd be a good thing to do. And if I did that, maybe I want that to come in. So if we did that, we would now have a pi bond here, still this remaining lone pair. That would create a positive where the electrons left. And then lone pair would be here. What used to be positive will now be neutral. And this double bond didn't move. So that's a reasonable resonance contributor. Now, of these two, this would be the better one because positive on N better than positive on O. So I'd rather have the positive charge on nitrogen than I would on oxygen. So either way, I'm going to have a positive charge. Okay, I'm going to try one more contributor and see if I can somehow get there. So the other contributor, if I'm doing this right, I want to see if this lone pair can push in. And that can go there. But if I did that, that would just end up giving me 5 bonds of nitrogen, which can't have. If I moved over here to oxygen, that would end up giving me 1, 2, 3, 4 bonds to oxygen. Can't do that, only wants 2. So these resonance contributors can't happen. Can only push directly here. So for this one over here, there's no major contributor. There's no significant contributor. There's only 2. Negative on, or excuse me, positive on the N and positive on the O. Okay, so let's go ahead and look at one more. A negative charge can end up on carbon. You'll notice the more of these you do, the more you recognize that charges end up at every other atom. So it was here, so it can end up every other. This one, if there was a lone pair that could donate in, so I could, in theory, try to move this over, but too many bonds. But if I could, it would have been there. But every other, so pos went from here, every other, so it's on the O. Negative charge here, every other could be on the S, or every other could be on the O. Again, always look for lone pairs becoming pi bonds and pi bonds becoming lone pairs. So here this lone pair is becoming a pi bond. If it goes to that side, then that O is going to go up. So if we did that, we now would have a pi bond here. And then I would have the original 2 lone pairs that I had, plus an additional lone pair for a negative charge. sulfur will end up with 2 lone pairs. Okay, so it could also potentially go the other way. So I'm just going to double up on this one. I'm going to draw it in green and yellow this time. Negative could have gone to this side, and in doing so, it would have had to have pushed the sulfur electrons up the sulfur. So if we did that, we would now end up with something that looked like this. It would have a double bond between carbon in the middle, and now the carbon on the left. My lone pairs would be sulfur would have its original 2 plus the one it just got, given negative charge. Oxygen would have its initial 2. Major contributors, minor contributors. Next thing to consider, a negative charge is on, no matter what, negative on O, negative on the C, and negative on the S. So everything is all octet. So let's see, 3 lone pairs in a bond, carbon set. This one, there's an H I haven't drawn in here, so I apologize for that, and I'm ignoring that carbon. But we're set here. This carbon's fine. 2 lone pairs, 2 bonds. That's fine. Same thing here. It's just the same thing we did here, but S and O reversed. So everything's set. Everything's got an octet. When I draw in the electrons on O and S, they have octets. So assuming octets are equal, you have a negative charge, you have to live with it. So we got to put in the best possible atom. The best possible atom for a negative charge would be oxygen. So this is the number 1 resonance contributor. Sulfur 2, carbon 3, based on their relative electronegativity. So oxygen can take negative, sulfur can take a negative, carbon doesn't really want to get the negative. Okay, so not bad. So up above, I should just reiterate that number 1 was what we started with. And number 2 would make the positive charge on oxygen for the upper one not as favorable. Okay, so again, pi bonds become lone pairs become pi bonds. I'm going to push that a lot. So the impact of reactivity and how resonance affects it, so the impact on reactivity. The most basic group, most basic oxygen, is the one that's going to be able to share its electrons most easily. And so this is one of the things you have to get used to, just trying to decide if the lone pair is tied up in resonance or not. So let's consider this one first. This lone pair and this lone pair are the 2 on oxygen. So if it's basic, we'll be able to donate those. But because of the pi bond right next to it, because it's allylic, I can put that there. I can move around. Maybe it ends up there. The point is, it can move the electron density around. So this one is tied up in resonance, which means if it's tied up in the rest of the structure, you can't share it as much. So that one's out. Okay, so let's consider a different one. This one, same story. This lone pair can donate in, go there, then go there. It can move around. So anytime you can donate a lone pair into the system, it's less available to be given away to acid coming in. Okay, so we move over here. Same story. This one can donate into that pi bond, so tied up in resonance. This one on this catechol can definitely donate in, get shared around. This one can also donate in. So far, it's becoming kind of a boring story. Everything's tied up in resonance. All the O's are adjacent. They're 1 carbon away or allylic to a pi bond, except for this one. And donates in, there's no pi bond that it's attached to. Because this carbon is not involved in the pi bond, this cannot donate by resonance, which means it's not tied up somewhere else in the structure. Therefore, it is the most available. So any of the OHs that have lone pairs tied up in resonance with the ring can't be given away as easily. So the most basic is this hydroxyl kind of by itself, not on a system with a pi bond. Okay, so hopefully this is starting to make a little sense. So again, we're going to just keep drawing structures, figure out where the most stable distribution of electrons lies, and we're going to ultimately just keep turning lone pairs into pi bonds and pi bonds into lone pairs. So which atom in the following compound is most likely to donate electrons to form a hydrogen bond? So if it's donating hydrogen or electrons to form a hydrogen bond, that means it has to donate electrons to a partially positive H. So if you're donating to a positive site, you yourself must be negative. So I can't see anything negative here, but let me go ahead and consider where my resonance is going to kick in. Lone pairs become pi bonds, pi bonds become lone pairs. So this time I'm going to start by withdrawing the lone pair, or the pi bond to make a lone pair. In order to offset that, nitrogen can donate in. Goes in the bond. If we do that, we end up with the methyl stays in the same place. We now have a single bond to O, but a negative. We now have a double bond to N, but a positive. And then we have the CH3 on the nitrogen. Okay, so if we're going to hydrogen bond, would you want to hydrogen bond at a site that's kind of negative? The minor contributor puts a negative on the O, or kind of positive. So even though I think nitrogen should donate electrons more readily, it is already donating them intramolecularly within this peptide, within this amide. It is donating electrons in, which puts electrons ending up on average on oxygen. So oxygen is going to be your most basic site. So this one is going to be the one most apt to form an H bond. Okay, so far so good. Each carbonyl bond is the longest in the following compounds. So once again, a question that can be looked at through resonance. This pi bond here has no lone pairs that can donate in. There's no lone pair here to donate in, no lone pair here. But this OCH3 of this ester at the end, I'm going to draw the lone pair here. Because I have a pi bond, I have a lone pair allylic to it, one away from the pi bond carbon. I can actually have this lone pair. I'm going to choose the upper one, but in theory, can do either one. Donates in. That will result in 1, 2, 3, 4, 5 bonds of carbon, so something has to break. So if I were to draw this structure now, I will notice I now have a double bond there. Single bond there. And then the rest of the structure just is the same. So this area right here is what's changed. So positive on the O, negative on the what used to be the carbonyl oxygen. So this can donate in. So that means that this carbonyl bond is part double and part single, which means it's going to average out to be a little bit bigger than a normal double bond. So if you recall, single bonds, sp3 to sp3 single bond, will be longer than sp2, sp2 alkene ceto bond Cs. So because this is part single and part double, so a bit longer, this one is, no matter what, just double the whole time. Double bonds are shorter, so this is your shorter pi bond, which means this is your longer pi bond. This is a pretty important feature. This is one of the things we're going to look at a lot more when we look at biomolecules. Which proton is most acidic on the compound below? So acidic, this is going to be an entire chapter coming up. So I'm sorry to spill the beans before we get to the next chapter, but trying to decide how acidic a proton is. So I want to look at all the candidates I have. I have a candidate here, I have a candidate here, and I kind of have a candidate there. The most acidic one is the one that's going to have electron density taken away from it. So the one that loses electron density, the one that loses a negative will carry the biggest positive and therefore be the most H positive, the most H plus or most acidic. So by resonance, these lone pairs donate in. So that's going to donate in. This one's going to donate in. That's going to cause this to go up. That would cause this to go up. So they're even so far. These two and these two sound pretty good. But the difference is over here. What's not drawn in is the lone pair on the nitrogen. Because that lone pair can donate in. This can donate in, causing that pi bond to go up. That means because of that one resonance contributor, this nitrogen being able to donate in, this electron donating group, you donate in, then this is O, this lone pair in O is going to go in less because you have this better contributor over here. If this goes in less, then you have less plus on that hydrogen. So if I were to look at the resonance contributors, when this goes in and this goes up, you have a negative up here. You have a positive on the oxygen with the H, so it makes it a little more acidic. So both the carboxylic acids are going to be more acidic than, let's say, a regular alcohol because of resonance, because of the withdrawal of the carbonyl. But this nitrogen, through this pi network, can donate in and ultimately put negative charge on the oxygen, so this lone pair doesn't have to be shared to do it. So this one is your number one most acidic hydrogen right there. This one will be a little bit less because that electron donating group. So electron donating groups make things more basic, less acidic. Electron withdrawing groups make things more acidic, less basic, less nucleophilic. Okay. So which nitrogen is the most basic? This is an absolutely critical, essential question that we have to get right because this is histidine, probably the most useful amino acid in terms of active sites that you'll find when you take bio classes or biochem. So I want to make sure I recognize which nitrogens are which. So this nitrogen has a lone pair here. This nitrogen has a lone pair here. The question is, are any of them tied up in resonance? So this one is going to donate in, and if it does, it can move it over here. And by doing that, that was going to give you this resonance structure. And the ends. Okay, so the question I'm answering is not directly what's been asked. I've done this, which makes this one a little more acidic because I just pulled this away. So this is my more acidic nitrogen, which means this negative that I have over here would make this the more basic nitrogen. So this one, electron density was pulled away. This one, electron density went to it. This would be a more basic site. And if I now I'm gonna twist it slightly. So apologize. None of the arrows are going to change very much, but I'm going to go from trying to decide if this is most acidic, that makes this one most basic, which is the question. And instead of answering the acid-base combination, I'm going to answer it straight out. This one's most basic because of the following. If this lone pair is donated to pick up an H+, then let me get rid of this charge over here. And I'm just going to get rid of this lone pair. This puts an H on here. The same resonance is going to help out because this lone pair here donated across, was able to pull the pi bond back, and this one can share its density. This lone pair is tied up in resonance with the rest of the molecule. This lone pair is actually not part of this pi bond. So there's one other picture I should draw. This is going to be kind of weird to see, but hopefully you'll be able to make some sense of it. If I consider these two nitrogens here and here, just consider the bond from a side view. I have this pi bond I have this carbon-carbon pi bond. And then I have an H sticking out here. But this lone pair on this nitrogen, I'm going to draw it in purple. This lone pair can also get tied up in resonance. So this system right here, these electrons 2, 4, 6 can all resonate around, meaning this lone pair is tied up in the ring. It's tied up in what's known as aromaticity, which is a special type of resonance, but it's tied up in the system. So because this one is tied up in the ring system, it is unavailable. On the other hand, I'll draw this in green. This lone pair is part of an sp2 hybrid. It is not tied up in resonance because it's perpendicular to the pi bond. Pi bond is the vertical plane, which means this is in the horizontal plane. That means this lone pair can readily be given away because it's not tied up in resonance. So two things you can do. You can look at the resonance of the acid or the base. So I chose first the acid, said this one's going to be made more acidic by this pulling away. So if this is more acidic, this will be more basic. Not the best route, but it does work. Then the second way I said, okay, let's just make it a base. If I donate this lone pair out to an H+, it is resonance stabilized, which means this is a little bit better base. But pictorially, hopefully this makes a little more sense. Is that this pi bond is right here, this pi bond is right here, and this lone pair is connected to all the other lobes. So it can be shared across. This lone pair can be donated into the system, so it's less available to give away somewhere else. This lone pair cannot because it's an sp2 orbital, said to be orthogonal, perpendicular, non-overlapping with the pi network. So this one can be donated readily. So when you deal with this, when you do amino acid chemistry, this histidine residue is going to be connected to the rest of the peptide, but this is your active nitrogen, the one that starts out with just a lone pair, the one that starts out as sp2. Okay, so how are we going to apply this down the road? So that this is kind of where this end of this chapter turns into the start of next chapter. So pKa's are a measure of how acidic a compound is. So just a quick rundown, like melting point tells me something about how tightly packed molecules are. Boiling point tells me how strong the intermolecular forces are and how heavy it is. pKa is like a physical property telling me how acidic a proton is. So their scale is can be pretty drastic. You can actually have a negative pK all the way up to a highly positive one, like in the 40-50 range. 0 to 14 is going to be the range we're most interested in for this class. So I'm going to say pK of 10. I'd like the pH not all that low, so it's kind of acidic. So phenols, because when you deprotonate, that negative charge can be shared amongst the benzene ring through resonance. It's a little more acidic than just a regular alcohol, but still not that terribly acidic. So we're going to look at resonance. Pi bonds pull away. So electron withdrawing groups have pi bonds. So if it pulls away, ultimately, it can steal electron density from that O, making this electron poor. Electron poor species, if they don't have negative, are going to be slightly positive. The more positive it is, the more acidic, the more that H plus can come off to alleviate the charge. Okay, so let me go ahead and let the structure get drawn in. So let me erase my add-ons here. And then let me just go ahead and put this lone pair that magically is going there. I should draw it in. 2 lone pairs on O. So lone pair can donate in, that goes across, that comes down, and that kicks out. So this is said to be an electron withdrawing group because it's part of the pi bond. Pi bonds pull away. Lone pairs turn into pi bonds, as we see here, turn into lone pairs. So again, it makes this end electron poor, which means it makes it slightly positive. It's more like H plus, it's going to be more acidic, give off an H plus more readily. The pK is lower than 10. So 10 is the baseline. When I pull electron density away, I make it more acidic, pK drops all the way down to 8.4. Okay, that's an electron withdrawing group. Electron donating groups, a lone pair, should tell me it's going to donate in. Lone pair donates in. That's going to make a 5th bond, so that moves over here. This one goes here. You can't make another bond to oxygen. Oxygen already has its 2 bonds and 2 lone pairs. So all you can do is move it in next to it. So let me go ahead and draw that resonance structure I just have up there. 6-member ring stays intact. Now have an O with lone pair and a positive charge. You have a pi bond here. And you have, I so apologize, I'm butchering this. So let me, so you still have this OH. You don't have any electron movement there. Here you end up with a lone pair, a negative. Pi bond here. And a pi bond here. So it's electron donating group. It put electron density in. You can't put a negative right on the H, but you can put it next to it. So because you added in, it's electron rich up here, you made it more negative. If it's more negative, it's less like H plus, it's less positive. So therefore, it's a weaker acid, pK goes up. Notice this went down by 1.6 because you took it directly from the O. This one only goes up by 0.8 because you're pushing it near the O, but not actually all the way to the O. But here's my reference point, electron donating groups. I'm gonna add density up here, make it a little less acidic, so pK goes up. Electron withdrawing groups, pull electron density away, make it a little more acidic, pK goes down. This is going to be an absolutely essential start or point to the start of the next chapter. We're going to play the game, rank those acids, where like this, we give you 3, give you a pK, and you need to guess the other pKs, or just say which is strongest, which is weakest. Okay, so more resonance. How does a CN group affect the pK of benzoic acid? So benzoic acid, 5.0 normally, but if I have a group here, pi bonds can pull away. So electron withdrawing group, if this bond pulls away, that'll take electron density there, which takes it there, which now makes this partially positive. If you put a positive on this end, you make it more like H plus, becomes more acidic, so the pK should go down as a result. So let me get rid of my electron withdrawing words here. First time attached is electron withdrawing, so when it pulls electron density away, it makes it go down. Hence, 3.4 instead of 5.0, and I'll go ahead and draw these here. So this resonance is going to put a positive here, so close to this group that it's going to feel the pain of it. It's going to be a little more acidic. So that pretty much covers resonance as a topic in of itself. We are definitely going to look at it in the next chapter, how it affects acidity, and we're going to see it over and over and over through the rest of OChem. So much so that you're going to hear me repeatedly say, what is the answer to every question? And pretty much in a good amount of time, you'll be able to say resonance. Okay, hope this went well, and see you at the next lecture, if I can escape out of this. Thank you.